Hey everyone, welcome back. Today we're diving into a groundbreaking approach to a big problem in data science, causal inference. Imagine you're a doctor trying to decide the best treatment for a patient. You know what happened when they received treatment A, but how do you know what would have happened if they'd gotten treatment B? This is the heart of causal inference, figuring out potential outcomes and counterfactuals. But here's the catch, real-world data is messy. Observational studies are full of confounding factors, variables that skew results. That's where tools like Gpmatch come in. It's not just another algorithm. It's a revolutionary framework that lets AI imagine alternative realities, like predicting what would happen if you'd taken a different career path or made a different life choice. Let's break down how it works and why it's a game changer for AI. Think of Gpmatch as a mathematical GPS for complex systems. Instead of guessing relationships between variables, it uses something called a neural ordinary differential equation, neural ODE, to model how data transforms continuously over time. Imagine you're watching a seed grow into a tree. Gpmatch doesn't just look at the final product. It maps every step of the process, like a reverse-engineered video of growth. This flow of data is guided by a velocity field, a mathematical blueprint that tells the model how to transition from one state to another. But here's the tricky part. To make these predictions accurate, the model needs to measure how well it's matching real-world patterns. That's where the CFM loss comes in, a kind of scorecard that tells the model, hey, your guess is off, adjust your parameters. This loss function relies on a calculation called divergence, which measures how much the model's predicted flow of data differs from reality. Calculating this directly, it's like trying to track every leaf on a tree, computationally heavy and error-prone. That's where the Hutchinson estimator shines. It's a clever shortcut that uses random noise to approximate divergence, like shaking a jar of marbles to infer the overall pattern without counting each one. By adding tiny random perturbations to the data and comparing results, the model gets a fast, accurate estimate. It's a bit like using a magnifying glass to zoom in on the big picture, simplifying complexity without losing precision. Now let's talk about the real-world impact. Researchers tested Gpmatch on datasets like ACIC and IHDP, which simulate scenarios with known outcomes, and even on images from CelebA, where it learned to generate counterfactual faces, like turning a male image into a female one or adjusting a patient's health trajectory. The results? Gpmatch didn't just keep up, it surpassed existing methods, learning in just 250 training steps. That's like mastering a piano piece in minutes instead of hours. Imagine a world where AI can answer questions like, what if this patient had received a different treatment? Or, how would this city look with green energy policies? Gpmatch is paving the way for these answers by bridging the gap between data and causality. It's not just about prediction, it's about understanding the why behind the numbers. So what's next? Gpmatch opens doors for applications in healthcare, economics, and even climate modeling, where understanding cause and effect is critical. It's a prime example of how AI is evolving from pattern recognition to true causal reasoning. If you're curious about the math behind it, check the paper. Trust me, the equations are as elegant as the results. Thanks for watching. If you enjoyed this deep dive, hit that subscribe button and let me know in the comments. What's one what if you'd love AI to answer? Until next time, stay curious.